got your active site. What's different here is the enzyme has an extra binding site. This is your enzyme. It has an extra binding site. And the inhibitor molecule is going to bind to the binding site of the enzyme. So that's your inhibitor. That's supposed to be an I. That's your inhibitor. Now, what this does when the inhibitor binds to the enzyme, it changes the shape of the enzyme. So you've got your inhibitor binding to the enzyme itself. The enzyme changes shape. The dotted line is just kind of showing where the active site was.
Right. And now it no longer fits in the substrate.
Exactly right. This no longer fits into the substrate. The shape has changed. Therefore, no reaction.
Does some reaction. The inhibitor.
Some reaction, yeah. It
So-
won't be zero, but it's basically stopped. Yeah.
Could that enzyme bind to the substrate without the inhibitor
Of
binding
course,
to
then
it?
that's an enzyme. Of course it would.
It would just have to be on the active site to bind to it. I'm not gonna do that.
I think you're making this too hard, but
No, I mean,
that's what enzymes do. But with the inhibitor, essentially, it's no longer an enzyme, essentially. Just change shape. And again, you guys have seen now plenty. Shape is a big deal. Yeah.
The inhibitor is not a protein.
No, I can't say that. Enzymes are always proteins. The question is, are inhibitors always proteins? Not always. In fact, quite often not. So, I can't even say. Inhibitors can be any of a variety of molecules, types of molecules. Enzymes are always proteins. But we can't do that with inhibitors. They could be almost anything. So at any rate, again, like I say, basically, it's no longer an enzyme. It doesn't fit anything. So the reaction doesn't go. Again, yeah, it goes a little, but essentially, it's been stopped. So that's not competitive. Because it's not competing with anything. It's just changing the shape of the molecule. So this, okay. Oh. So, it binds to another part of the enzyme. It's called allosteric inhibition. Allosteric because the enzyme is changing shape. Now, once again, the question can be, can it change back again? In this case, quite often not. I can't say 100%, it might change back, but a lot of times it does not. Most of the time it does not. So it's kind of permanent.
I don't follow about the allosteric.
Well, allosteric means shape change. The molecule changes shape. That's what allosteric means. So allosteric inhibition is the enzyme is changing shape to this. So that's why it's called allosteric. It's making the enzyme change shape. See, that was not the case with the competitive inhibitors. Nothing changed shape. But here, the enzyme is changing shape. And that's allosteric. Allosteric inhibition. Allosteric, we saw before with chemotaxis, it refers to shape change. Usually, an allosteric molecule can change back again, but not this time. Let's do some examples here. Yeah, I think I want to keep that. Let's just do some numbers that I'll make up.
What are we
Let's say,
I was gonna say, what example are we doing?
inhibition.
Okay.
Let's say we have 10 enzyme molecules and 10 substrate molecules. So you would expect each enzyme would bind to a substrate. So you would expect something like this. A star means activated molecule. The enzymes bind to the substrate. You're essentially activating the substrate, and then you get a reaction. But it's 10 to 10. You expect everything to bind to everything. But now let's throw in an inhibitor. Let's throw in an inhibitor. So 10 enzymes, 10 substrates, 10 inhibitors. Now by random collisions, i.e. playing the odds, you would kind of expect half the enzymes to bind to the substrate, half to bind to the inhibitor. Just by random collisions, random chance. So you only get 5 enzymes binding to the substrate. And 5 would bind to the inhibitor. So this would be a case where the inhibitors result in the substrate. And so on. So that's your inhibition, because before you were getting 10 reactions, now you're only getting 5 reactions. It's still going, but it's going a lot less. Now the question that I'm going to throw at you, I don't expect an answer, but the question I'm going to throw at you is, how can you tell whether or not you have a competitive inhibitor or a non-competitive inhibitor? So I mean, that's a rhetorical question. I don't expect an answer. But the way you can differentiate between a competitive and non-competitive inhibitor is to add substrate molecule to the solution. Add lots of substrate to the solution. Now by lots, I don't mean double or triple. I mean like 100 times substrate. And let's do that. So 10 enzyme, 10 inhibitors, but now I'm going to add 100 times the substrate. So I'll be adding 1,000 substrates. So to differentiate, greatly increase the substrate concentration. What you'll be looking for is if the reaction rate increases, you have a competitive inhibitor. If the reaction rate does not increase, if it doesn't change, you have a non-competitive inhibitor. So let me repeat that, because that's definitely on the tricky side. To differentiate whether you have a competitive inhibitor or a non-competitive inhibitor, add substrate, add lots of substrate. If the reaction rate increases, you have a competitive inhibitor. If the reaction rate does not change, then you have a non-competitive inhibitor. So there are two obvious questions here. One is, how does it work? I mean, what exactly does that mean? And second, I'm talking about the reaction rate increasing or not increasing. How do you measure reaction rate? How do you know if the reaction rate is doing anything? So one thing at a time, let's first take a look at how does this even work? Why is the reaction rate increasing with a competitive inhibitor? Well, we've added 1,000 substrates. So again, random collisions. You've got 10 enzymes, you have 10 inhibitors, and 1,000 substrates. So which molecule is the enzyme most likely to bind to? Yeah, it's going to be the substrates. You've got 1,000,000 times more, not really 1,000,000, but you've got a ton more substrates than inhibitors. So the chances are very, very high. You'll probably get all 10 enzymes binding to the substrate. Now, it is, again, just random collisions, so it doesn't have to be 10. Maybe you'll get 9 and 1. You know, anything's possible. But the point is, the chances are extremely high. You're going to be getting a lot more enzyme binding to substrate. If you have more enzyme binding to substrate, you would expect more reaction. That's why the reaction rate goes up with a competitive inhibitor. So the obvious question now would be, well, why doesn't it go with a non-competitive inhibitor? What does that part mean? Well, think it through for a second. Let's say you do have a non-competitive inhibitor, and then you add your substrate. What actually would happen in this case? Therefore, exactly, you got it, you nailed it. Exactly right. With a non-competitive inhibitor, you are changing the shape of the enzyme. The enzyme is not going to fit into the substrate. You can add all the substrate you want. The enzyme is still not going to fit. That's why the reaction rate does not increase with a non-competitive inhibitor. Essentially, you no longer have an enzyme. So all the substrate in the world doesn't change that.
But is it a guarantee that if you have 10 enzymes and 10 non-competitive inhibitors that all
It's never a guarantee.
will bind to
It's never a guarantee. You're playing the odds. Let's just say the odds are very high. That's all you can look at. I tell you, normally in the research lab, whatever you're doing, you wouldn't just do it once and publish. You would do it 10 or 15 times and then publish. So over a number of tries, yes, it should work. So again, the reason a non-competitive inhibitor does not change the reaction rate with more substrate is because essentially you have no more enzyme. Essentially. Therefore, the amount of substrate doesn't matter. Is that clear? Is that okay for everybody? Okay. Well, let's go to the other part of this. Then I'm going to erase this if everybody's okay with it. Is how do you know? You know, the reaction rate increases, it doesn't increase. You know, nobody's going to tell you that. If you're in the lab and you're trying to measure reaction rate, nobody's telling you. How do you know? Actually, we have to go back to that. So our reactants are colliding with each other and producing product. So what you do, and this part varies, what you can do is take out a sample every 10 seconds, every minute, every 10 minutes, whatever. It varies. Let's just say every minute. So every minute you'll take out a sample from your solution, and then you measure the concentration of the products. Now clearly, the longer the reaction runs, the more product you should be producing. So you measure the concentration. So you should be getting something like that as time goes on. And this reflects the increasing concentration of your products. Now let's say that you add substrate. Now you're going to test and see, well, what kind of inhibitor do you have? So you add substrate. If it takes off like that, that tells you you have a competitive inhibitor. If nothing happens, that tells you not competitive inhibitor. So it's still increasing, your reaction's still going, but it didn't change. That tells you not competitive inhibitor. So we've added substrate at this point. You still have a question?
I just don't understand the incline.
Well, again, your reaction is running. You know, you're taking out every minute, every whatever. So your reaction is running. The longer the reaction runs, the more product you should have. That's what a reaction does. It produces product. So,
That's without an inhibitor.
well, you might have the inhibitor. You're still getting a reaction. It just may or may not be very much. So we're assuming there's an inhibitor here. The but you're still getting some reaction. But
The incline was due to what?
you've got a reaction. The reaction produces product.
Makes sense to me, but I would think it'd be more like steady, that's how I'm like, I
Okay.
understand what
Okay.
the
I can do
incline
that.
was.
I can do that.
Okay.
So this will be with your inhibitor. So it doesn't have to be this, I just did it. It could be like this, and then you add your substrate, and then it might go like this.
You're adding that substrate.
Or